phone on silent, huh? Okay. Let me start attendance. Okay, so attendance is going, so if you want to check in on attendance, y'all can go ahead and do that. Oh, I stopped it. Why did I stop it? I'm going to delete that one. Just go ahead and do it again. I meant to click the blue circle and not the red one. Do it again. I'm so sorry. So sorry.
My clicker is not working.
Your clicker's not working. Are you in the classroom or at home?
I'm at home.
Try, is it on a phone or is it on a handheld device?
It's an app.
It's an app. Close it and completely.
Yeah.
Okay, so let me close this. And which clicker question did we finish on? This one. Okay, I think we're ready. Okay, so I wanted to share a few things with you real quick. I think I fixed the iCloud, so you shouldn't be getting notifications at 2 a.m. anymore. Some people were. I'm sorry. Technology, we're all figuring it out. Okay, so I think I fixed that. So if you do still have problems, let me know. The other thing that a couple of people were asking me was, where can we find some extra videos and things like that on the topics? Oh, I didn't start the video? Okay, I'm sorry. Lillian, if you, but you check in. I think, Lillian, you're okay. I don't know, we have to check, but we can check at the end of class. All right, they were asking for extra videos and things like that on the topics that we're covering. So if you go to the chapter 3 material where you got your lecture slides and go all the way down, these are all my videos, but I also made a separate Word document that has extra videos that I found on YouTube that look good. So you can use these as you need them. You don't have to, but I wanted y'all to know that they were there. Okay? All right. Any questions before we start? All right. So let's do a quick review. Full screen. Okay. So this is one we did last time, and we knew magnesium sulfide, right? Okay, so now let's start a new poll. What is the name of the compound CaNO32? Okay, 5 seconds. Okay, so what do we say? CaNO3 2. So what you should have gotten, I can do this, is D, and that's what most of y'all got. So when we look at this, where's calcium on the periodic table? Is it a metal or is it a non-metal? If it's on the left-hand side of the periodic table and it's in blue, I think it's in blue in your periodic table, let's see. Yep, the metals all are blue. So calcium's a metal. NO3 is a polyatomic ion. We see it in parentheses, that's a big red flag. So if we have a metal and a polyatomic ion, it has to be an ionic compound. So how are we gonna name it? We're gonna name the metal, and then we're just gonna give the name of the polyatomic ion, right? So calcium nitrate. And you just had to make sure that you had the right, is it nitrite, nitrate, or nitride? Nitrite, ITE, is one less oxygen, and nitride is off of the periodic table. So be careful with that ending, that you know what the different endings mean. Okay? Britlin, your clicker points, so at the end of the semester, I'm going to total up all the clicker points, and if you have 70% or higher, then your participation points will be full credit. So you'll have 150 participation points. So if you look at my syllabus, it has all of the details on it, but your participation is 150 points. So if you get 70% or above, that will give you all the points. If you go down, it's a 10-point scale down. So if you want to see the details, you can look on the syllabus or you can send me an email. Yeah, Lillian, we gotta figure out your clicker before our in-class time. So we can't figure it out during class. Okay, the next one. What is the formula unit for sodium phosphate? Sodium phosphate. Okay, 5 seconds. Okay. So what you should have gotten, I don't know how to move this, is you should have gotten E. So if we're looking for sodium phosphate, sodium, we just look on the periodic table. We know that that's a cation, it's a metal. It's in group 1, so it's going to have a charge of +1. Our phosphate is a polyatomic ion, so you had to go to your polyatomic ion table. That would be a good thing to have, right? In addition to a periodic table next to you. PO4, 3-. So you do your crossover, and you get Na3, PO4. The 1 is understood, so we don't have to write it. So it should have been E. Okay. All right. Now you have to select the incorrect name formula pair. So which one is it not correct? Now be careful, we've got some different kind of compounds here. Okay. Oh, I should have said 5 seconds, so you got 5 seconds. Okay. So what you should have said good was B. B is sulfur dioxide. Well, what should I have written if I had sulfur dioxide? SO2. But as it was written here, it's sulfur trioxide. What's different about all these compounds from this question versus the last question? Look at the last question. What kind of compounds are these? These are ionic. We have a metal and we have a non-metal, or we have a metal and a polyatomic ion. But when we look here, and that's right, we have covalent compounds. How did you know that these were covalent compounds? 2 ways that you can tell. You have the prefixes in the names, but what else? What's the definition of a covalent compound? 2 nonmetals. Awesome, y'all. Awesome. 2 nonmetals. Okay, so let's see if I can trick you. One more. Here we go. Which compound is ionic? Okay, 5 seconds. Okay, so what did we say? Which compound is ionic? C is ionic. How did you know C was ionic? Calcium is a metal. As soon as you see something that's a metal. So anytime you're looking for something ionic, you're looking for a metal and a non-metal, a metal and a polyatomic ion, or the last thing, it's not very often, but a polyatomic and a polyatomic. Those are the cases where you will definitely have an ionic compound. Okay. Somebody said, are the clicker questions posted on Moodle for you to review before the exam? No, but every class is recorded. And so you can go back to any of the recordings and check out the clicker questions that way. Okay, so I want to switch gears and we're going to go and work on our in-class problems. And then if we have some time at the end, we'll come back to some more clicker questions. Okay, so how far did we get? I think we finished 3.31. Let's see. 3.31. We did 3.31. Wait, we were doing the odds or we were doing the evens? 3.35. Come on. 3.3. Not 3.35. We didn't get that far. 3.34. Okay, that's where we're picking up. All right. Okay, so this should be easy because we just talked about this, right? We were talking about, no, hold on, I forget how to do this. Full screen, but then we want to do this one. All right, now we could. We want to know whether our compounds are covalent or ionic, right? Okay, K2O. What do you think? Ionic, why? Because we have a metal. Anytime you see a metal, I want you to think ionic, right? Really quick and easy way to identify. CO2, what do we have? Metals or non-metal? It's all non-metal, so what must it be? Covalent. GaF3. So you have to go and find it on the periodic table, right? So that might take you a minute, but once you find it, you would know that Ga is a metal, so it has to be ionic. C2H6 has to be covalent. I don't have any metals in there. NiCl2 has to be ionic. Nickel's a metal. BaSO4, ionic. Barium's a metal. SO2, covalent. N2O, covalent. There's non-metal and non-metal. NH4Cl. I hear both ionic and covalent. What is NH4? It's a polyatomic ion. So anytime you have a polyatomic and a non-metal, it is ionic. SiH4. Si, what kind of element? Metal or non-metal? It's a metalloid. It's a metalloid. So if you're looking at your periodic table, right? If you look for Si, right, you're going to see it's green. Every periodic table colors in different colors, but it is green here. So if you have a transition, not a metalloid, not a transition metal, but a metalloid, then you're going to name that an ionic compound. Okay? I'm sorry, you're going to name that a covalent compound. Why did I say that? A covalent. So if it's green or if it's yellow, covalent. Okay? SiH4, covalent. Good? All right, let's see. Oh yeah, and here's my video mistake. Here was my video mistake. What did I do in the video? Were y'all paying attention? Some people were. Some people told me. Right? I named H2O dinitrogen monoxide. Is that right? No, it's not right. Come on, Dr. B. It's dihydrogen monoxide. What's the common word for it? Water. But if you want to freak people out, just tell them you're drinking dihydrogen monoxide. It's not, it's water, but it'll still freak them out. All right. So we're given the formula, we need to supply the name. N2O4. Dinitrogen. So di for 2. And then what's 4? Tetra, but we usually drop one of the vowels, so we just say tetroxide. Because it's kind of hard to say 2 vowels together. All right, carbon monoxide. How do I write the formula for that? CO. So if there's nothing in front of the first element, what do we have to assume? Just one. P2O5. Diphosphorus. What's 5? Pentoxide. So we drop the A off the penta. Carbon dioxide. What's our formula? CO2. Okay, NH3. Nitrogen, because we don't have to say anything if it's the first one and there's only one of it. So nitrogen. What's 3? Tri. And hydrogen, we say hydride. Anybody know the common term for NH3? Ammonia. Good cleaning agent. All right, let's see. We can move on now, on to section 5. So this is what you should have started watching, right? You watched 5, 6, and 7, right? Is it 7 in this one? I always forget. Yeah, 7. Okay. So now we're really switching gears. We're back to some conversion factors, and we are back to dimensional analysis. So remember I said it wasn't going away? It's really not going away. I wasn't lying. All right, so we want to compare the number of atoms and the number of grams present in 1 mole of helium and 1 mole of argon. So if we're going to do that, you have to do dimensional analysis. So you need to pick out of your question what you're starting with and what conversion factors you're going to need and where you're going to go. Okay, so for our first half, right, our goal is to find the number of atoms. And what are we starting with? We're going to start with 1 mole of helium and 1 mole of argon. So let's do helium first. We're going to start with 1 mole of helium. Okay. If I'm trying to get to atoms, what conversion factor do I need? Well, I know I'm going to have to put moles on the bottom, right? So I can at least put that. What am I trying to get to? I'm trying to get to atoms. Is there a conversion factor that you know that relates moles to atoms? Yes. Yes, you should. What is it? 6.02 times 10 to the 23rd atoms of helium per mole of helium, right? Remember that's Avogadro's number? 6.02 times 10 to the 23rd is a mole. So is anybody interested in a mole of M&Ms from the video? that was a lot of M&Ms, right? We don't need quite that many. So if I've got this all set up, can I do the same setup for argon? If I have 1 mole of argon, I'm going to use exactly the same conversion factor, but it's argon. 1 mole of argon. What's my answer going to be? It's the definition of a mole, right? We really didn't have to do the math on that, but it proves the point. You have 6.02 times 10 to the 23rd atoms of helium, and you have 6.02 times 10 to the 23rd atoms of argon. So it says to compare. How do these two compare? They're the same. They're the same. All right, I'm going to have to go down to the bottom, right? But we're going to do the same thing. We're going to compare moles. I guess I'll just erase it. Y'all got this one? If I erase it? All right, y'all are awesome. I really tried to put more space into the next chapter, so I hope that works out for us. All right, so now we want to know the number of grams present. So this is our new goal. We're going to start out with 1 mole of helium. How are we going to get to grams? I need to look on the periodic table, right? When I look on the periodic table, there are always 2 numbers in any given element's little square, right? The atomic number on top, and then we have the atomic mass on the bottom. So what does that atomic mass tell us? It tells us the number of grams of whatever element it is per mole. So I know for helium, I have 4.003 grams of helium in 1 mole of helium. Is it important in these dimensional analyses for me to write helium after each thing? Is that part important? It's super important. Because if you switch from an element to an element inside of a compound, something like that, that we might do later, you're going to get yourself confused if you don't write it. So when you write your dimensional analysis, put your unit and then make sure you put what element you are talking about. Okay? So what do you get? Grams of helium. Okay, let's do the same thing with our moles of argon. If we go and look at argon, here's argon. I have 39.95 grams of argon in 1 mole of argon. And my moles cancel. So all I'm left with are grams. So I have 39.95 grams of argon in a mole of argon. Are they the same? No, no. Why are they different? Because of their mass. What is the mass of an atom due to? Two things. Protons and neutrons. So tell me in helium, how many total protons and neutrons do I have? How many protons in helium? 2. How many neutrons in helium? 2, right? And we're not talking about all the different isotopes. We're gonna assume there's only 1, just for the sake of discussion, right? So how about argon? How many in argon? 18 protons, and then how many neutrons? Another guess what? 18, right? So which one is going to be more massive? Which one is going to have more mass? The one with more protons and more neutrons. That makes sense. You have more stuff inside of it, so it's heavier. Okay, so that's why it's different. We good on that? Okay. All right. Calculate the following. The number of sulfur atoms in 0.660 moles. Okay, so we're going to start out with 0.660 moles. And this is our goal here. My goal is to get to atoms. So if I want to convert from moles to atoms, what am I going to do? I know I need moles on the bottom. I'm going to go to the periodic table. I'm going to find my element, and what am I going to do? I'll say in 1 mole there are Oh, I'm going to grams. Why am I going to grams? I'm sorry, y'all. I'm going to grams. Where are we going? Atoms. So how do we get to atoms? The 23rd atoms in 1 mole. So what do we get? Move this over. Ooh. Put it in your calculator. What do you get? You can put it in the chat. It's going to be a pretty big number. 3.97. How many Sig Figs? 3. We have 3 significant figures. So 3.97 times 10. Whoa. Times 10 to the what? 23rd. What are my units? Atoms of sulfur. Okay. All right, so now we want to do the same thing, but we want to do it for copper. So in this case, we're starting, oh no, we're on B. We're starting with grams of iron. So here's B, grams of iron. So we have 15.0 grams of iron, and we want to know number of moles. So now I'm going to put grams on the bottom. How do I convert to moles? So I'm going to find iron, right? And I know in 1 mole of iron, I have 55.85 grams of iron. So my grams cancel. I'm left with moles. What do we got? I got 0.269. Is that what y'all got? 0.269. What are my units? Moles of iron. So how small are atoms that you have 15 grams of something and you don't even have a mole of it, right? 0.269. That's telling me that my atoms are very, 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 very small, right? So kind of keep that in mind, keep that perspective on the size of things. Okay, yesterday I was able to go down. Why am I not able to go down? Oh, well, that's okay. All right, so the next one says number of atoms, right? Number of atoms in 66.0 grams of copper. So what am I starting with? And I'm trying to get to atoms. So I know I want my grams to cancel out. So what do I do? I know in 1 mole of copper, I have how many grams? Y'all tell me, because I'm not looking now. 63.55 grams of copper. Is this where I want to be? Ooh, not yet. I got to keep going. Keep going. So my grams canceled. I'm left with moles, but I want to get to atoms. So I'm going to put moles on the bottom. What do I know about moles and atoms? Times 10 to the 23rd atoms in 1 mole. Okay, what do you get? Put it in the chat. What do you get? It's always important to look back at the question and to say, did I get the unit I was going for? Because a lot of times one of the answer choices on the exam will be maybe moles, right? So maybe you started the problem, but you didn't finish it. So be careful with that. So what do you get? 6.25 times 10 to the 23rd. And my units are atoms of Cu. Okay. All right. I can see I'm going to run out of room again. So I might just have to do one and then erase it, do one and then erase it, okay? All right, so determine the molar mass for the following compounds. What is a molar mass? Yeah, so if you look at any given compound, it's going to have a particular formula, right? And so this one, in the first one, we have C2H4. So we have carbon atoms and we have hydrogen atoms. And so we have to take into account the mass of the different elements and the number of atoms of the different elements. And that's how we calculate a molar mass. So it's the mass of that formula, right? Okay, so how do we do this for A? What are we going to do? I think I left my formula up here. So what do I have? I want to go look at carbon, right? So what do I know about carbon? So because I have C2H4, so I have 2 carbons. So I'm going to look at my mass of carbon because I have 2 atoms. I can multiply by the mass. And what else do I have in this formula? 4 hydrogens. And so if you go look and find hydrogen, hydrogen's right here. What's our mass of hydrogen? Our atomic mass? 1.008. So if you multiply 2 times 12.1 plus 4 times 1.8, what do you get? 0.5, is that what y'all got? Okay, what are my units? So this is in grams per mole of C2H4. That is correct. That's how many grams of this particular substance are going to be in 1 mole of that substance. Okay, let's do B. C6H8O7. So I have 6 carbon. We just found out carbon was 12.01. We know hydrogen, there's 8 of them, and we know that's 1.008. What we don't know is oxygen. What is oxygen? 16.00. So what is my molar mass? I'm going to go ahead and erase A so I have room for C. Anybody? 192, not 99, 92.12, and what are my units? Grams per mole of C6H8O7. So typically, we look at, typically all of your molar masses on here, I think most of them go, ooh, some of them only go to 1 digit. It depends on the periodic table, how far they'll go, but it just depends on how much space is there. It's not really, you really have more significant figures than that. They've measured it. But typically we'll go at least 2 places past the decimal when we give a molar mass. But you can base it on the significant figures that were given. So here we have 4, here we have 5, here we have 4. So our answer you can give to 4 would be fine. Okay, sodium bicarbonate, NaHCO3. How many sodium do I have? 1. What's my molar mass for sodium? 22.99. Plus I have 1 hydrogen, 1.008. Plus I have 1 carbon. We said carbon was 12.01. Plus we have 3 oxygen. We just said oxygen was 16.00. So what is our molar mass? .0. I got 0.1. Do I get 0.0 or 0.1? Okay, 0.1 grams per mole of, and we're going to put our formula, NaHCO3. Okay. Everybody got that one? All right. Determine the number of molecules in a 200 milligram dose of ibuprofen, and we're given the molecular formula C12H18O2. We haven't talked about molecules yet, but when we use Avogadro's number, does it have to be atoms? No, it could be molecules, it could be M&Ms, it could be cans of soda, it could be anything, right? So remember that Avogadro's number just tells us that we have that many things in 1 mole of that thing, okay? So what are we starting out with? We have 200 milligrams of C13 H18O2. Okay, it's going to be a long dimensional analysis. Can we go directly to the molar mass? Why not? Good catch, y'all. Very good catch. You have to convert from milligrams to grams. So what do I know about milligrams and grams? Milli means 1,000, and there are 1,000 milligrams in 1 gram. Okay, so my milligrams cancel. Now what do I know about converting from grams to molecules? You can't go straight to molecules. What do I have to do first? I have to go to moles. I call it Mole Town. Did y'all hear me on the video? Mole Town. I had somebody even draw like Mole Town for me. It's just such a hip place that everybody wants to go through Mole Town in order to get to molecules, in order to get back to grams. It's just a hip place. All right, so if we want to know grams of C13H18O2, we know we can go and get that from the periodic table. So C13H18O2. So how do we calculate that? Oh, I feel like I can't scroll down. Why can't I scroll down today? That's so sad. Okay, I'm going to do it at the bottom in red. So if I go to the periodic table, I need 13 carbons. What's carbon? 12.01 plus. I need 18 hydrogens, 1.008. Plus, I need 2 oxygens. Oxygen is 16. So what do you get? I'm going to put it right there. 206.274. What y'all got? And it doesn't really matter where you round. You don't have to round at this point. Wait and round at the end. Don't round your stuff in the middle. Always wait until the end. Okay. Oh, but we're not done. What do we still have to do? Are we in the right unit? No, we're in moles. And what do we have to get to? Molecules. How do we do that? 1 mole C13 H18O2. We have 6.02 times 10 to the 23rd molecules of that same thing, C13H18O2. So what is your final answer? I'm going to draw it. I'm going to write it at the top. 5.849. There's got to be some times 10 to the something. It's a really big number. Times 10 to the 20. And that is molecules of ibuprofen, which is C13H18O2. How about Sig Figs? Now, I'm going to tell you honestly, what should the number of Sig Figs be in this answer? Your book did a terrible job. It should be 1. Because is there a decimal place behind this 200? No. So your answer really should be 1. What they probably meant to do was put a period there so that you would have 3 significant figures. But according to this, you should really only have 1. So we'll go ahead and assume that there were 3, and we'll put that decimal place and we'll round, and that'll become a 5. Yeah. Okay. All right. Got all the math out of our system? Feeling good, right? No? Practice. My thing with that is practice. The more you practice, the more comfortable you're going to feel with it. And y'all know about the extra practice problems at the end of your chapter. And you can check your answer on the odd numbered ones. So if you go to the end of the chapter, at the end of every single chapter, we do all the problems at the end of every section. But then at the end of the chapter, what you see are, oh, I'm not far enough. Here we go, additional problems, right? And you see how they're blue and black, the numbers? The blue ones are the odd numbered ones, and if you turn answers to odd numbered problems, you can know if you're on the right track or not. And if you keep getting it wrong, please send me an email and say, please set up a Zoom, I need some help. These are the problems I was doing and I'm not getting it, right? So I'll help you out. I'm happy to help you out. But that way you know where you're struggling and where you're not. Or you could take a picture of your homework, a screenshot of your homework. I'm working on this and I, for some reason, can't get it. I need help. All right, I'll help you. Okay, so now we're going to talk about covalent compounds. So far, we've talked about covalent compounds being basically flat on the paper, right? But that's not how anything exists in real life. Real life is three-dimensional. So we have to start thinking in 3 dimensions. And it's going to be important for the next chapter as well. So you have a sheet of paper, right? You can't show something in 3 dimensions. So we have to have some kind of a notation to show 3 dimensions. And so what we do, instead of doing just a line for a bond, is we're going to do some different symbols for bonds to show whether it's coming out at you or going away from you, right? Because we can see X, we can see Y, we can see up and down and left to right, but what we can't see is the Z axis, which is like towards the board or that way, okay? So what's the difference between the solid and the dashed? What does our solid mean? It's coming towards you. So it's in front, right? So this chlorine atom that's attached with this solid triangle is telling us that that atom is coming out of the paper at us. Okay? Now, how about the dashed line? I know it's not an orange atom, but how about the dashed line? What is the dashed line telling us? It's going beyond the plane of your paper, of your computer screen, whatever it is you're looking at. It's going behind it, right? So tell me about the other chlorine here. What's this one? It's actually in the axis. It's in the axis of the paper. Okay, so this is in the axis or the plane, the paper, screen, whatever you want to think about. Right? Okay. How about our chlorine down here? This red chlorine. This one is going behind. The plane. And then how about our hydrogen here? In the axis. So you need to be able to interpret a drawing and know how it looks in 3 dimensions, sort of. All right, let's see. Okay, for the molecules in 3.46, determine the shape around the central atom. So that's this one, right? So for B, what do we have around B? What is this one? How do you know it's tetrahedral? There are 4 areas of electron density. And remember, electrons, they don't like each other, right? They're the same charge. They want to get away from each other as much as possible. So if you have 4 things, the maximum distance that you can get away is 100 and what? Remember your bond angle? 100. What? 109.5 degrees, right? And everybody is the same bond angle. They're all getting as far away from each other as possible, right? So this is tetrahedral. Tetrahedral. How about my nitrogen up here? How many bonds does that nitrogen have? Only 3. But is that the only areas of electron density? No, I actually have 4 areas of electron density. So both A and B have the same number of areas of electron density, but what's different about A than B? A has a lone pair. A lone pair aren't held as tightly together because they're only attached to one atom. Atoms inside of a bond are shared by two atoms, so they're kind of constrained as to where they can go. They have to hang out between the two atoms. But a lone pair is only attached to one atom, so it ends up spreading its wings and making itself comfortable, right? Getting as far away from the other electron in that electron pair as possible. And so what happens is it pushes down on the other bonds. And so it kind of squeezes them, right? So what happens to the bond angle when we go from B to A? Now A has a bond angle that is less than 109.5. You don't have to know exactly what number it is, but you have to know that it gets a little bit smaller. So what's our shape? Pyramidal. Okay, so your shape changes because you went from having 4 bonds to having 3 bonds and a lone pair that kind of jam things together. Okay, let's see. All right, determine the shape around the orange colored atom or atoms in each of the following Lewis structures. So let's take our first carbon in B. How many areas of electron density do we have? We have 3. 1, 2, 3 areas of electron density. Do we count that double bond as 2? No, because that's, whether it's a single bond or a double bond, all the electrons have to be in a particular space. So you only count them as 1. So if it's a single bond, that's 1. If it's a double bond, that's 1. If it's a triple bond, that's 1. So we have 3 areas of electron density. Do we have any lone pairs? No. So what shape is this going to be? This is going to be trigonal planar. And this is 120 degrees. Right? We only have 3 areas of electron density, so we have a little bit more space. Remember, if we had 4, it was 109.5. Well, now that we're down to 3, we got a little bit more space. How about my second carbon here? What about my second carbon? How many areas of electron density do I have? 1, 2 areas. What is the maximum distance that these sets of electrons can be to get away from each other? 180 degrees. So what do we call that? Linear, right? It looks like a line. That one's like the easiest one. It looks like a line. So we call it linear. They're side by side. Okay. Oh, did I not do them? Oh, I guess I didn't do B in the video. I should have done B in the video. That's okay. All right, let's do it again. Dimethyl ether. So we're doing the same thing. We're determining the shape around the orange colored atom or atoms. All right, let's do the carbon first. How many areas do we have? 4. 1, 2, 3, 4. Are they all bonds or do we have some lone pairs? All bonds, so it must be tetrahedral. Now let's look at our oxygen. How many areas of electron density do we have? We have 4, so we have 2 bonds, 1, 2, and then 3, 4 are lone pairs. So you got to remember that these lone pairs take up so much more room than a bond. So remember, if we had 4 areas and no lone pairs, we were tetrahedral. What happened when we went from 4 areas and 1 lone pair? What were we? Right, we had 4 areas. Where did we do that? And 1, this one right here is this yellow, this one right here. That's pyramidal. Okay, so what happens when we go to 4 areas and 2 lone pairs? We have a bent structure. So what it really looks like is water, right? And these, it's like you have your hydrogens, right? And so you actually have these lone pairs that then push down on those bonds, right? And so they get smaller and smaller and smaller. So we say like less than 109.5, right? We said tetrahedral is 109.5, pyramidal less than 109.5, less than 109.5, and then we say bent is less than 109.5. So you don't have to remember all the numbers. You just have to know that it keeps getting smaller and smaller. Yes, well, it's around the highlighted atom, right? Because there's not one central atom in this molecule, right? You got carbon, oxygen, carbon. So it just depends on which atom we're looking at and count around that atom. Yeah? Okay. Ethylene, a plant ripening hormone. Let's look at that first carbon. So this carbon right here. How many areas? 3. 1, 2, 3. Look at the second carbon. How many areas? 1, 2, 3. So they have the same conformation. Excuse me, what is it? Trigonal planar. And that's 120 degrees. So you say both. Okay. All right, last section. Last section. Electronegativity and molecular polarity. So you will need your electronegativity table from the book. It looks like a periodic table and it's got numbers on it, but it just has the electronegativity value. So if you have your computer, pull it up. I should have put it on here, but I did not, okay? All right, so for each of the following molecules, draw the correct Lewis structure, label polar covalent bonds with dipole moment arrow, and then determine if the molecule is polar or non-polar. And then draw the dipole moment arrow for the molecule. So we got a lot to do on this one, right? All right, so let's do A. CH3Br. Question is telling you that carbon is a central atom. So if I put carbon, how many valence electrons in carbon? 4. Okay, and then we have 3 hydrogens and 1 bromine. So I'm going to put hydrogen, hydrogen, hydrogen. How many valence electrons in hydrogen? 1 each. Now how about bromine? 7. 1, 2, 3, 4, 5, 6, 7. What do I need to do to complete my octet for all my atoms? Well, it's not. There are not all octets. We have some duets. We're going to make some bonds, right? So if I make 1 bond with a hydrogen, hydrogen's happy. So let's do that. What do we need to make carbon and bromine happy? One bond. So if I count around bromine, this is 2, 4, 6, 8. So that's good. If I count around carbon, 2, 4, 6, 8. Carbon's happy too. Could do the needed available shared if you want. Doesn't make a difference. Right? Okay, so we drew the correct Lewis structure. Label each polar covalent bond with a dipole moment arrow. We usually go to our electronegativity table. What is my electronegativity value for carbon? Carbon's what? 2.4? 2.5. What is hydrogen? 2.2? 2.1, that's what I thought, 2.1. Okay. How about bromine? 2.8. So as you're reading in the book, what the book says is that carbon and hydrogen's electronegativity values are so close together that we basically say that they share the electrons equally. Even though there's a difference, we see that there's a difference, but that difference is negligible. And so we can basically say they have approximately the same electronegativity values. So do we have a polarity in a carbon-hydrogen bond? No, we say that's a nonpolar bond. So anything that's a carbon and a hydrogen is nonpolar. So that's a nonpolar bond, here's a nonpolar bond, and here's a nonpolar bond. Right? I don't have to do anything. But tell me about my carbon and bromine. And I shouldn't have written all over my beautiful drawing there. Right? It should be carbon, hydrogen. So tell me about carbon and bromine. It's got to be a polar bond because we have an electronegativity difference. So if we look at that electronegativity difference, which one is more electronegative? Which one is so greedy that it wants more time with those electrons? Bromine here is more electronegative than carbon. So whichever one is more electronegative is hogging that electron for a greater amount of time. So if that electron spends more time around bromine, what's the charge on that electron? It's going to be negative. So if the electron spends more time around bromine, that bromine is going to be partially negative. So bromine is partially negative. What's going to happen to the carbon? If the electron's spending more time with bromine, I initially started with an equal number of protons and electrons, but one of my electrons is hanging out over there by bromine. So what's my charge going to be? It's going to be partially positive. It's not a full positive, but it is partially positive. So remember, when you're drawing dipole arrows on bonds, what you want to do is point at the negative element. So if I have an arrow, I'm going to point at my negative element. My negative element is bromine, and then I want to put a plus sign at the end of the arrow to indicate my positive atom, partially positive atom. So what is my overall now dipole moment of this molecule, right? This was just the bond. But what's going to be my overall moment for the whole molecule? I have to take into account all my bonds. It's still going to be the same direction, right? Because we only have one polar bond. If we had more than one polar bond, it would be different, but we only have one polar bond. So the red one's for the molecule, the blue one's for the bond. Okay, then we have B is HF. I think I'm just gonna have to add a page and y'all will just have to tell me. So B is HF. So first we have to draw our Lewis structure. How many electrons in hydrogen? Valence electrons, 1. How many in fluorine? Fluorine wants 8, but it doesn't have 8. How many does fluorine have? Fluorine has 7. So how can I complete everybody's octet? Or duet? Make one single bond, right? Y'all told me the electronegativity value of hydrogen was 2.1. How about fluorine? Fluorine the floozy, y'all like that? Fluorine the floozy, she will take electrons from anyone. Anyone, she is the most electronegative element. That's how I've always remembered it. And it stuck with me, so I'm hoping it sticks with y'all. What is it? What's the fluorine's electronegativity value? 4.4? Y'all, it's hard for me to hear with all this. 4.0? Thank you. 4.0. I can draw a 0. All right. So what's my more electronegative element? Gotta be. It's gotta be that floozy. It's gotta be fluorine. Okay, so I'm gonna draw a dipole moment for my bond only, and I'm gonna point at my electronegative element. What's my electronegative element? Fluorine, and I'm gonna put a little plus on the hydrogen side. So now tell me, how about my whole molecule? I only got one bond, right? So it's the same thing. Poor fluorine. I've picked on fluorine for years. She'll get over it. All right, C, we have PBr3. Okay. So how many valence electrons in phosphorus? 4, and we'll put our double up here. It doesn't matter where you put them. How about bromine? 7. PBr3. Did I not say? Is it PBr3? Yeah. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, what am I going to do to complete some octets? I want some single bonds, right, between bromine and phosphorus, okay? Does everybody have a complete octet? Yep. Now that we know about the three-dimensional shape of molecules, is this really a good diagram of this molecule? No, it's not. Why? They're not all in the plane of the screen, right? Why not? Because one thing, we have what? A lone pair, right? So they're not at right angles either. So how should we kind of draw this? We need to put them kind of going at angles, right? But what else should we also think about? One's going in, one's going out, right? So it doesn't matter which one you do. And we can change this to that little dash thing. I'm not very good at drawing that, right? And then we can put our bromine atoms. Don't forget your lone pair on your central atom. Okay, so now, what are my electronegativity values? Phosphorus, 2.1? Bromine? Okay, so who are we pointing at? We're going to point at bromine. So we got to do it for all of our bonds that are phosphorus and bromine. So what's my overall dipole moment going to look like? One big arrow kind of in the middle. I got that one. We got one left. And then we're going to do a few more clicker questions so y'all can gain some more points. Okay, D. OF2. What's my central atom? Now we can do this. Whenever you're drawing these structures, your central atom is going to be your least electronegative atom. So who's the floozy? Fluorine's the floozy, so she can never be a central atom. She's just not going to happen. So oxygen has to be my central atom. And then I'm going to have 2 fluorines. So how many valence electrons in oxygen? 6. 1, 2, 3, 4, 5, 6. Fluorine, how many? 1, 2. So how am I going to complete my octets? Going to make some bonds. Now, knowing what you know about molecular structure, is this a good diagram? It's not. Why? I've got lone pairs that are taking up a lot of space. What does this molecule have a similar shape to? Water, H2O, right? We listed the hydrogen first, but it doesn't really matter what you list first, right? We know that water looks basically like this with these big electron clouds. Well, guess what? It's the same sort of structure. So you're going to end up with the same shape. What shape is this? This is bent. Right? So this is bent. Okay, so now we need to do our dipole moment. So tell me about oxygen. What's oxygen's? 3.5, fluorine 4.0. So who's more electronegative? Fluorine, we're going to point at fluorine. We're going to point at fluorine. So what's our overall dipole moment? They're pointing in opposite directions, but they're both pointing kind of down. So the left and right kind of cancel out, and we're pointing down. Okay, we got 9 minutes. We're going to do a couple of clicker questions. I'm going to try and get your clicker question rate up. Okay, so 16. These should be easy now that we've done all this. Use full screen. Let's see how many we can get in a few minutes. This should be super easy. How many dots are in the Lewis structure for a bromine atom? And don't forget your homework is due on Monday. Homework is due Monday night at 9 p.m. And I'll have up, I started putting up stuff for chapter 4, so that should all be up by the end of the day. How many dots are in the Lewis dot structure for a bromine atom? Y'all, these are clicker points. This should be some good clicker points, right? I'll give y'all to 1 minute. If you have a periodic table, it'd be good to use it. 5 seconds. Okay, so what did we say for bromine? You should have 7, good. We know that bromine's in group 7A, so it must have 7 valence electrons. How many valence electrons are present in this entire molecule of PCl3? So now we're going from just one atom to the entire molecule. How many valence electrons present? Okay. 5 seconds. Okay. So what did we say? You should indeed have 26. So how did you get 26? Phosphorus has 5, chlorine has 7. So 3 times 7 is 21 plus 5 gives you 26. Okay. If you draw a Lewis dot structure for PCl3, that's the one that you just did, and select the correct description of the central atom. So which one of the answer choices correctly describes the central atom? I'll give y'all 2 minutes on this one, because you have to kind of draw it. We almost had everybody's responses. I said I'd give you 2 minutes. Okay, 5 seconds. Okay, so what you should have said, good, was B. B. So if you drew the Lewis dot structure, what should you have gotten? Something that looks like this, right? So you could have done needed, available, shared, or you could have done it the way we were doing it earlier today. Either way, this is the structure you should have gotten. Okay. All right. So draw the Lewis dot structure. Here's a new molecule, CS2, and select the correct description of the central atom, CS2. I'm gonna call it at 2 minutes. So you still got 35 seconds. I'm gonna give y'all one after this, because we still got 2 minutes, so you can squeeze one more in. The more chances you have to earn these points, the higher your percent's gonna be. It's a good thing. Okay, 3 seconds. Okay, so what you should have picked, oh, we had a big range here, so you should have picked A on this one. So when we talk about, ooh, here we go. What structure are we looking for? So your carbon is going to want that complete octet, so it's going to make double bonds with the sulfur atoms. So we had no lone pairs and then double bonds. Okay, very, very last one, I promise. Last one. Which of these compounds is classified correctly between molecules and formula units? Hint, hint, what's a molecule? Covalent or ionic? And what's a formula unit? Covalent or ionic? And I really am calling it a minute because everybody's chomping at the bit to get out. 5 seconds. If you haven't run in, please run in. Okay. So which one is classified incorrectly? You should have picked A, right? It's classified, oh, correctly, not incorrectly. Correctly was A. Everything else was opposite. All right, y'all have a great day. I will see you on Tuesday. Don't forget to submit your homework between now and then. And Lillian, are you in the class or on Zoom? Because we need to work out your problem.
For the molecule problems, the molecules might help.
Are you in radians or degrees?
I'm in degrees.
Which one was it? What number? I think, okay, wait, Lillian say. Doesn't work when I'm at home, it only works when I'm in class. I don't know about that, Lillian. I know that the app will work at home and in the class, but I don't have a lot of experience with the handheld clicker. So maybe that's what it is. Maybe that's what it is. If you know of anybody else who uses the iClicker, if they can use it at home. I thought it was on Wi-Fi that it would work, but I don't honestly know. So ask somebody else who uses the iClicker. You can put it in the class discussion board if you'd like and see if somebody would answer it. Can I set up with you? Yes. Yes. Send me, go to the Moodle page. Oh, no, that's not the right Moodle page. Go to the Moodle page and then to make an appointment, right here is the appointment calendar. So just click on that and you can make an appointment with me and I'll help you set up the iClicker. Y'all good? Okay. So, which number? Okay, so what you're probably doing is not putting this in correctly. So type in 200 times, and what I would do is I would open parentheses. Okay. 6.02. And then when you want to do, what did you, no, you're going to do raise to the 23rd. So when you're doing that one, And then you're going to divide by 1,000. And then divide by 206.27. So I don't either you weren't putting this in right, or you're doing the top, and then you go divided by 1,000, but you don't press enter, and then you press divided by 206.274, and then it flips it. So do the top divided by this, hit enter, and then divide by that. Yeah, of course. Okay. All right, good. I'm gonna go ahead and end the Zoom then.